So let me start with some preliminaries just to get things out of the way, because I'm going to talk about Hahn fields again. I want to make sure that I have to set up the notation because, you know, sometimes people are additive, multiplicative. And I forgot to say, of course, I absolutely thank the organizers for inviting me to speak. And I also thank you, the audience, for coming here the morning after the social dinner. So I hope it wasn't too bad yesterday night. I left early to be prepared. Okay, so I'm going to talk about joint work with, now there's a bit of a long list, Alessandro Berarducci, Michael Matuszynski, and Salma Kuhlman. And for some reason it's still in progress. It's been actually ages. But I think that the plan is that we want to finish this next week and put it up. Okay, so first of all, a bit of setup about Hahn fields and chronologies. Okay, so first of all, so notation we're going to use. So small k is going to be a field possibly ordered. A, B are going to be ordered sets. Sometimes they're going to be actually groups. So Z, G, H, etc. ordered groups. And when I write K double bracket A, I mean all the functions from A to small k such that the support of the function, so the points where the function is not 0, is reverse well ordered. Okay, so the support is going to have a maximum, and then every non-empty subset is going to have a maximum as well, not a minimum. So I'm writing things in this way. And I'm going to call this Hahn vector space. Okay, vector space. Okay, so that's, and the notation for this function should be using different colors since we have them. The notation for this f is going to be the one you might be familiar with. The sum over the elements, sorry, of A, the elements G in A, the monomials of fg, the sum coefficient, f of g, which is the value of the function, times g. Okay, and of course I say vector space because clearly there is a natural notion on sum of this on this object and multiplication by scalar, just the pointwise multiplication. Okay, and now I have to make a decision. Yes, great. Something like this. No? Perfect. Ha. Okay, then when G is a group, so fact that, I mean, especially if you've been here for the program, I mean, you should really know this. When G is a group, so the notation up there, then K of G is a field, which we call the Hahn field. And yeah, And then another piece of notation, definition as you want. For f in Ka, K double bracket A, the, shall we say, norm of f is the maximum of the support of f if f is not 0, and 0 otherwise. Okay, so this is evaluation, except that I'm writing this in the multiplicative way. So I want to make sure that we have no confusion about how this behaves. So this is a function from Ka to A, and it satisfies the ultrametric inequality. So norm of x plus y is less than the maximum of the norm of x and the norm of y. Okay, so that's how I want things to be. Okay, and then let me make the usual example. Form a Laurent series, an example of this. Okay, now maybe some people cannot see this, but I know who is there, so I know you don't need it. Okay, so I take a multiplicative copy of the group of integers z, multiplicative copy. That's why I added a t here in this case, and that gives me a Hahn field. Okay, so that's for the usual stuff. Any questions so far? Any objections? No, no objections. Okay. Okay, so let's come now to the second part, these Bernoulli's. Why do I say Bernoulli's? Now that's probably something less familiar. So the problem is, well, the title of the entire program contains the word trans-series, and trans-series means I'm dealing with power series like this, but you also have exponential functions and logarithms. But something that has been mentioned already a few times during this workshop is this one. There is no exp on kg. Now, what do I mean by no exp? Let me make this precise, because the assumptions are very limited, i.e. no function such that, and now the properties are just that exp, well, the usual exp is an isomorphism from kg plus to kg greater than 0 times. Okay, so from the additive group to the positive part of the multiplicative group, and isomorphism. And then the other one is, I need to say that there is at least a bit of compatibility between this Hahn field structure and the exp. So we want the exponential of k of g less than or equal to 0, which is, let's hope I'm phrasing this the right way now, because I don't want to say residue field anywhere. Okay, so I want the things that have norm at most, 1. Oh God. And tripping over this myself, so that's not good. So the things of norm less than or equal to 1, which would be the finite elements in certain settings, they must go to finite elements, okay, and vice versa, and leave this as well. Okay, there is no function doing this, and the proof, actually, I can give you a sort of condensed version of the proof, very condensed. So let me remind you, this is the Kuman-Kummer-Scheller result, 2008. No, before? No, Salma is not sure. So somewhere in the 2000s. Okay, let me be vague. I think this is now. I mean, it's common knowledge now. I mean, it's well known. Okay, so how do I do the proof? Well, I fix a sequence of monomials. Yes. This one. Well, this is multiplicative group. Yes. Yeah, let me write this somewhere. I had it on the notes, but I skipped this. So when I say all the group here, so let's have it on a more visible. I always have this in mind. 1 times. So written multiplicatively. Okay, so I hope not to erase that board because it's a reminder of how I'm writing things. Okay, so I take a sequence of monomial, fix a sequence. Monomials, I take some G naught in G greater than 1. So an infinite monomial in G. And then I take Gn plus 1 such that also in G greater than G such that Gn plus 1 is greater than 1 again, and it's less than the norm of log of Gn. So it's a decreasing, well, I'm not saying it's decreasing necessarily, but I just want this Gn plus 1 to be no more than the log of Gn. And not just of log of Gn, but of the leading monomial, the norm of Gn, the log of Gn. So the first monomial appearing in this series. Okay. And then I define G and alpha. Alpha here is an ordinal now to be equal to, well, so now the argument is, I didn't say that, I mean, suppose that there is an exp such doing this, and now I do exp of minus sum over beta less than alpha of G n plus 1 beta times Gn. Okay. So inductively, I start from, I have this sequence here, and then I define another sequence by induction over alpha, and that's it. And now the delicate part is that to define Gn, I'm using the Gn plus 1s, but only for beta less than alpha. Okay, so as an induction, it works. And now what happens is all these guys are positive and they get smaller and smaller. So this sequence here is made of, so all the monomials in this sequence are going to be, did they say monomials? I think I forgot to say, I need to add this. Okay, to make sure it is a monomial. And that's it. And now exercise, verify this sequence Gn alpha is going to be a class-long sequence of monomials, of distinct monomials in my group. But the group is a set. That's a contradiction. So this is an induction over the ordinal alpha that just never ends. Okay, exercise, feed the details, check what's going on, but it all comes from this. So there's really there's a big obstruction really coming from, if you have an exp, then you have to come up with something like this. Of course, the paper is more sophisticated. The paper does a more general argument, which is more tricky. But I mean, for the purpose of this talk, this is enough for me. I mean, right now, just to make my case. Okay, so how do we get around this? So you have seen Lie series or trans series in several, during talks. You've seen some real numbers, many of you. But even if you haven't, I would be surprised. But still, now the solution, quotation mark, is to replace the full Hahn field Kg is something a bit smaller, okay? Something that is a union of Hahn fields, but it's not a Hahn field itself. So this is take unions of Hahn fields. Okay, so in the case, example I keep mentioning now is LE series, which are these, and now this is tricky because I don't want to define them. Okay, so I'm just going to say LE series are a certain union. In a typical presentation is a union over two natural numbers of certain fields. Oh, I should use G. I was using letter G. There is a certain family of groups increasing in both indices, and one index goes up whenever you add more exponentials, and the other index goes up whenever you add more logarithms, more or less. Okay, just to say, and basically by doing this union, then you guarantee that the structure is closed under exponent log. The end result is not a Hahn field. Okay, it doesn't contain all possible public series. So in this case, has x log. So you construct it so that that's an exponential function. But for example, the typical thing is that the sum of the iterated logarithms of the monomial x is not an LE series. Okay, because it doesn't belong to any of these groups. I mean, these monomials, they each belong to a different group in this stratification. And so you never get to see these actual series here. Okay, so now I want to make this into a nice formal object that I can reuse and use it, you know, to use the same language to describe all the examples. So let me define a Bornology is just a name. Okay, I'm taking this from Bourbaki, of all people, is an ideal, and I'm going to use, I hope you're not going to hate me, I'm going to use curly G in the power set of G, of group G. Group G or the set A, I mean, it doesn't matter, the group structure doesn't matter. I mean, there is really, this is just about a set, the set G. It's an ideal, okay, ideal, by ideal I mean, if A, B belong to G, then the union belongs to G. And if A is a subset of some B in G, then A is also in G. Okay, so you can go downward and you can take unions upward. Okay, also, and this is just a technical requirement, I'm going to assume that this ideal G of subsets of G covers all of G. Okay, and you fill in the fonts between what I just said. Okay, so then that's, and now basically this is just you know, one way of writing now directed unions of Hahn fields. So I'm going to write K G with subscript curly G to be the union of a in curly G of K double bracket A. Okay, so bit of notation. Let me give you a couple of examples. So one example is definitely LE series up there. So that family of groups. So LE series. So let GLE be this union over Mn GMn. Now, I wish I had a subscript up there for this, but anyway, I hope it shouldn't be ambiguous. So let this group this guy G curly G ideal generated by the GMNs, and then LE series are just going to be the Hahn field. Oh, sorry. LE series happen to be done over the real numbers, but nobody said anything. So can I blame you? No, no, probably not. Anyway, I'm going to write it like this. Okay, it's the subfield of this Hahn field given by the union over this particular family. I should probably write G and E here as well. But it's a specific one. Okay. Then another example is kappa bounded Hahn fields. Which normally will be written like this, where this kappa now is a cardinal, and this would just be, now I have to come up with some way of writing this. This would be the idea of the subsets of G of cardinality less than kappa. Okay, so this is P kappa G is a subset of G of cardinality less than kappa. Okay. I'm saying subsets, okay? In fact, I'm going to make a comment in a moment about this, in case you're wondering. And another example is the surreals. Okay, the surreals. So typically, you're going to see people write something like this. Okay, I will absolutely not define what this is, even if you ask. But then, if one wants to be precise, there should be some bound here, okay, in the same style as this one. Why? Because because the only series that are allowed to appear in serial numbers are the ones who support is a set and not a proper class. Okay, so there is an implicit bound on this, and I can write this in the same style as we write kappa bounded series. Okay. Anyway, the good thing is that this kind of object you can do exp and log here, so it works. Okay, so that's for part one. Okay, again, questions or objections so far? No. Okay, everybody is happy, or at least quiet. Okay, now let me go to the meat of the talk. I want to start here, which is strongly additive. And actually, I'm just going to do linear maps. For simplicity, I basically, I will avoid specifying, whether something works with additive rather than linear, because the interesting cases are the linear ones. Okay, and this is a delicate point. I mean, some of you were thinking, oh, I know what he's talking about. There are tiny subtleties in the way we define this. So I'm going to give you a definition, and that's going to be my definition, because it does. It seems to be the one that works. Okay, so basically now the point is, again, if you're familiar with this is well known, but these Hahn vector fields are groups of infinite sums, and then you can also try to take infinite sums of infinite sums. Okay, and that's this strong linearity, and so you want to talk about things which are linear, but in the strong sense that they respect infinite sums. So what's an infinite sum? So let me start from the basics. Take some family AI of elements of Ka, for I, an index moving in some set. Okay. And we say that this is summable when two things must happen. So first of all, I want to take the sum of these guys, and I want the sum to be still here. So first of all, I want to check that the union of all the supports of the AIs is still reversal ordered. Okay, otherwise I have no chance of getting back into Ka. Okay, so the things in Ka must have support which is reversal ordered. Well, no chance. There's another technicality there, but I will. Nobody ever complains about it, so I'll just leave it there. But basically, I want to guarantee that I'm going to be back in Ka right away, and then I want that for each monomial in A, the set of i's such that the monomial G appears in the support of AI must be finite. Because the idea is I'm doing some coefficient, term by term, and if the same term, the same monomial G appears infinitely many times, then I'm going to try to sum infinitely many coefficients. But nobody tells me I can do infinite sums in small k. K is just an abstract field, and maybe then, I mean, if you do the reals, then you can do convergence, but that's not in this setting. I mean, that's not what we want to do. Okay, so when we have these two conditions, then we define the sum AI to be sum for G over G. Remember the notation up there in yellow of, let's see if I can write this right. Sum over I in I of AIG, I'll tell you in a moment what this is, times G, where AI itself is, each AI is written in this way. This up. So if AI is a sum with these coefficients over G, then this is how they find the infinite sum. And now you can see that to make sense of this, you want to have those two conditions, because then condition 2 tells me that each of these sums is actually a finite sum. Most of it is 0, so you can throw it away. And then you have finite many things to add together. Okay, so this is summability. And now I want to do this linearity. Okay, I have made a strategic mistake. Anyway, too late. Because I don't want to cover this one, so I can't use the third blackboard. Okay, well, let me give you at least one example. I mean, just to make sure we're all on the same page. Whenever you write a formal Laurent series in this way, and now I'm going to do a terrible sin, minus infinity of t to the I, something like this. That's, I'm thinking of this notation as the sum of a summable family. So the family is indexed by all the integers from n to minus infinity of these guys. So this is sum of the family t to I for I in Z. So let me write it in this way. The interval is minus infinity n in the integers. Okay, because it's not, I mean, this is now a notation method. It's just that it wouldn't be exactly be written in this way. Okay, but this is a technical thing right now. It's not, just to say, that's a trivia. That's a very easy sum family. The support is, you can check that the support is reversible order, the union of all the supports. And each monomial, in this case, appears only once. So definitely you satisfy this condition too. It's all very easy to check in this case. Okay, now, well, now we have a notion of infinite sum. So let me define the span of the talk. What does it mean to be strongly linear? Let me, well, strongly additive. So let V in K A B K, well, again, subgroup. I said that, let me say strong vector space, K vector space. Okay, F from V to some other KB, another Hahn vector space. And we say that this is, sorry, linear, K linear. And we say that F is strongly linear when the following happens. Now, for every AI, in capital I, summable, the sum is, so for every summable family of elements of V, so take AI in V, in a summable family, you can take the sum in Ka in the Hahn vector space. If the sum is back in the vector field V, then F of the sum of the I is equal to this, the sum of the F of AI. Okay. And that's my definition. Period. Okay. Typical examples. I have to do this, don't I? Examples. Examples. Derivations. I mean, not all of them, but you know, known derivations. I mean, how do I say? No, derivation on E. So the derivation on any series is of this kind. Then the simplest derivation on the surreals. And when I say simplest, I mean, you know, the one we were doing some time ago. Now, if you've seen the talk by Van der Hoeven last week, then you know that there's also another one, which is also canonical in a different sense, in a stronger sense, which is also the same type. Okay, but that is so new that I don't want to. I'm sure it is. I mean, it is of this type, but I haven't read it yet. So, okay. So these are typical functions that we use that have this property. Okay. Now, why something delicate about this definition? So one note. I set it up in a special way because F from V to Ka is strongly linear if and only if it extends to a strongly linear f tilde from all of Ka to Kb. Now I'm afraid that making this statement, I am. What? No, it's not B. Oh, the codomain. Yeah. Sorry. Yes. And now when saying this, I think I had to add one assumption, which is when V contains all the monomials. It's always going to be the case. So I'm happy to work with this restriction. So I'm making this point because I had this. I take a summable family in this V, and then I say, when the sum is in V, then I have this rule. Basically, this is already, it imposes so many restrictions already on its own that actually you can apply. The idea is that you can apply F even if the sum is not in V, and you can make sense of the value of F outside of it, and that's how you produce this extension. It's yes. Yes, because I have this assumption. Yes, thank you. Uniquely. Okay, now there is a skepticism because yes.
It's probably a stupid question, but if I don't understand, if V is key of A, there is no obviously F extends to P of A. So that means that F is always strongly linear.
No. I mean, it's because the word strongly linear is also on the right hand side of this equivalence. So if V is equal to K of A, this is a tautology. I'm just saying F is strongly linear if and only if it's strongly linear in that case. So I'm just saying, I mean, sort of the interesting, the sort of the example I have in mind is that, so the example for this comment, and that probably clarifies a bit why I'm making it is, for example, you could take V to be just I mean, this is not even the algebra, just the vector space. How do they call this? This is the direct sum of copies of K for each point in A. I mean, it's just a vector space. Okay, this thing contains only finite sums of monomials. Okay, but if I say that so you might think, and that's actually what we thought was the case, is that, well, being linear or strongly linear was, the same thing, and it quickly doesn't make a difference. Actually, it does. So linear does not imply strongly linear, even if you only have finite sums, for some very stupid reasons. That when you take the summable families, you basically you can always make this become zero. So you start with some arbitrary, strange, complicated family, infinite family, and infinite sum. Then you take the same sum with a minus in front of it. You make a huge summable family, and the sum is zero. And zero is here. So when I look at the definition tells me I must be able to still make sense of this stuff. So yeah, so the fact that V is small basically has no bearing it doesn't make things easier. Being strongly linear really means you're actually coming from a functional entire Ka. Yes.
Yeah. So if you have a map like this that you just drew here, right, this F from the group ring to KB, let's say, are we saying that there might be cases where it does not extend at all, or,
Yes.
or that,
Oh, yeah.
or that the extension, there always is an extension and it's not unique, or both things can happen?
No, the extension is not strongly linear. Yes, so I can say there can be the F linear with no strongly linear extension. Well, said it this way to anyway. Actually, the point is that because this is if and only if, as soon as you're not strongly linear, then there is no strongly linear extension. But of course, there's going to be a linear extension in many of them because of this is a vector space. You take a complement and So linear algebra is easy. Strong linear algebra that puts some restrictions on what happens. Strong ones. It's a strong condition. Okay, so now strong linear maps. Basically, you can forget about the vector space and just think about them in this way, in this setting. But it's still nice to have the notion because it's subfield, sub-vector spaces come up. The bounded ones are the kind of these I'm thinking about. Now let me show you some results now. Okay. Because now the question is what we have is so let's sort of give you the motivation first. So the typical thing that happens in LE series, real numbers, etc. One of the first things you do, you put this derivation on. Derivation is a strong linear map by construction. That's how you define it, and then you prove it has a section in these cases. So there's this whole asymptotic integration and then integration business. You find that there is an inverse. And something we realized is that in the literature, it's not quite written anywhere that the integral is also a strong linear function. I guess that maybe you knew already. But I don't know. I think it's not quite written. So proposition. So let me tell you at least when this kind of thing works. So let me give you first a bit of a special case, but almost the full thing. So suppose B is truncation closed, and if you don't know what that means, don't worry about it because I'm not going to prove it anyway. So I ask you to accept it. And then you have this F from B to KB strongly linear. And suppose that it is, and now suppose also that it's weakly valuation preserving. I'm going to tell you in a second what this means, but I want to add injective here right away because then I'm going to make a change on that. So valuation preserving here, I mean, if the norm of X, valuation of X is greater than or equal than the valuation of Y, then the valuation of f of X is greater than or equal to the valuation of f of Y. Okay. Then the inverse of f from the image of f back to V is strongly linear. Okay, it's a linear map because the vector space is injective maps. They have inverses, but it's also strongly linear. It's not complicated to prove. I think it's one page, maybe, our proof. It is a bit tricky. So the people who played with this stuff, I mean, we do it with batch sequences again. So there's a bit of a combinatorial thing in the style of some of the proofs of the Neumann's lemma for some ability. At least that's how we do it. I mean, I'm sure that there will be other strategies. The point is, it's a short proof, but it's a bit delicate. At least that's for us, at least. Okay. Now I cannot apply this right away to derivations, because derivations are, the interesting ones are not injective. They have a kernel. Okay. So what does happen when there is a kernel, and which one do I want to use? This one. Wow. Okay, so well, I do this on the spot. If I remove injective from here, then I need to make a couple of changes. First, I have to change the meaning of, I mean, I have to be more careful here about valuation preserving. I think I want. Now, this is not the same way we've been writing it, so I'm really hoping that when preparing this yesterday, I did not make this wrong. But yeah, you want to verify this equality, this inequality, unless the x is close to an element of the kernel. Okay, well, in that case, that this equality wouldn't quite make sense. And then I don't require that this is injective, but I need some information about the kernel, otherwise things don't quite work. So I want that the kernel of f contains its own monomials. Okay, so it is a bit of a technical condition. For example, if oh, okay. Usually the kernel is going to be truncation closed. I mean, actually, in most cases, the kernel is just the constant, it's just the field k. So definitely it works in this setting. Okay, if I have this, then now, of course, I cannot quite use f inverse, because f is not injective in general, but there is a restriction to a certain complement of the kernel, which you can use, and that's mostly linear algebra. So I'm not going to tell you what the complement is. I mean, you can read the paper, which I promise next week will be finished. Okay. So now let me get onto this. So I want to make an example. Let's see, because I'm actually over time. So let me tell you what the plan is. I'm going to give you an example of how this works in real life, and then I'll mention how to make it work for bounded things, which are which I did hide behind this black box. So you have to remember what it was. Okay, so examples of applications, so to say. The usual derivations on LE series, so real numbers. As I was saying, they're strongly linear. The kernel in this case, so the kernel of these derivations is always just the reals. So you do satisfy condition 2. So the support is going to be just the monomial one, and it's there already. They are strongly linear. So since they are surjective in the settings, there is an integral map from LE back to LE, and also from NO to NO. But this is strongly linear. Okay. Then another comment is something that Michele said on Wednesday. What if you're working with an automorphism of a Hahn field? So if sigma kg and kg is a strongly linear valued field automorphism, okay, I need valued field automorphism because I need to have this condition 1 here. Then the inverse is also strongly linear. So I understand when in his talk he was saying I take the group of strongly linear automorphisms, and he was saying strongly linear both sigma and the inverse. Actually, the inverse comes out of 3, at least in this setting. Okay, now I want to finish sort of with the claim and then one other application if I'm quick enough, which I'm never going to be quick enough, of this. So how do we make sense of this in the bounded setting? Well, in the bounded setting, in bounded setting, we have statements like this. Basically, at this point, I'm more interested in, okay, so now we understand when the function is, has a strongly linear inverse, but now I want to know when is the function surjective? Okay, and this is where it gets more delicate. So I'm going to write these 2 statements. One is, let's make this in an increasing progression of complexity. So the first one is an easy exercise. So work with this kind of strongly linear maps from V to KB. If V is contained in, if the image of your function f is hitting all the monomials in your codomain, then f of Ka is equal to all of Kb. Okay, so you're going to cover everything. Easy exercise, okay, do a couple of lines. Now let's make this more interesting. If B is contained in the norms of the things in the image of F, then, oh, this is scary. Then again, this is going to be surjective. Okay, and if you're familiar with this is the asymptotic integration argument. Okay, just written in an unusual way, maybe. Okay. Now, how do I make sense of this in the bounded setting? Well, in the bounded setting is it's a bit different. Because now the image is not all KB, is going to be maybe some bounded thing. So say F goes from Ka, and then there is some Bernoulli here to KB. There is some other Bernoulli here on B, with all the assumptions as before. And then we have a statement that reads like that. If F is bounded, and is the F inverse restricted to this complement is bounded, and then we have and then there's the complicated one, F composed with non-composed with F inverse is something we call uniformly bounded. Then F is surjective. I'm going to stop, I promise. I have a statement like this. Okay, and this is and basically you could in principle take it. You take the derivation on any series, for example, and you check that these three things are true, whatever they mean, because I haven't told you. And then you get automatically that F is surjective. Okay, so it's, I don't know, it's convenient language, then we use it. Now I don't get to show you the example because I'm way over time. I will use it to show that, I mean, our particular application we had in mind, the thing we wanted to do was, oh, suppose I have some strange derivation from some Hahn field, some abundant Hahn field like this, and we want to build, want to construct a logarithm out of it. And all this machinery is convenient to do that, and we managed to improve on some previous results on Sam and Michael, and then we get these weird objects where the derivation should not exist because they don't satisfy T4. Okay, this is super technical just for a couple of people in the audience. Okay, I'll stop here. Thank you.
So, since the next talk is starting in 2 minutes, we will postpone